In this video, I'll be going over benzene reaction part 3. So the first reaction we're going to be looking at is Friedel-Crafts Alkylation. So if we react a benzene with some kind of alkane chain with a chloride or bromide at the end and react it with AlCl3 or AlBr3 if we're using bromide instead, then what ends up happening is that this methyl or this alkane chain is going to be directly substituted on the benzene as shown. So much like all benzene reactions, it follows the same 3 steps. The first step is generating the strong electrophile. So if we have some kind of alkane chain, in the previous problem we use CH3Cl and react it with AlCl3, then this mechanism is very similar to halogenation, in which this chlorine is going to be attacking this AlCl3. And once that happens, we end up getting a molecule that looks like this: CH3Cl plus AlCl3. What ends up happening next is that this electron is going to go onto the chlorine, thus producing CH3 plus with some kind of ClAlCl3 molecule, or more commonly known as AlCl4. So this electrophile is now a strong electrophile in which it can do the direct benzene substitution. So as we know, the next step is doing some kind of benzene attack, in which we have a benzene, like so, and we have our strong electrophile. In this case, it's CH3+. So like all mechanisms, this electron from the benzene is going to attack the CH3, thus producing this intermediate. Right? And now we have a plus charge here. So like with all reactions, the last step is doing some kind of elimination reaction. Keep in mind that we still have AlCl3, as well as we also have 1 hydrogen on this benzene, like so. So very similar to any halogenation reaction, this electron here is going to attack the hydrogen, and the electrons on the hydrogen is going to be reforming aromaticity, like so. So once you draw out that mechanism, what ends up happening is it results in a molecule that looks like this. We have reformed aromaticity, we have a methyl group bond, and we also have ClH or HCl, as well as AlCl3. However, keep in mind our main product that we're looking for is this. So the last reaction we're going to be looking at is Friedel-Crafts Acylation. If we have a benzene and react it with AlCl3 as well as some kind of carbon chain with a double bonded oxygen as well as a halogen, very similar to Friedel-Crafts Alkylation, this part of the molecule basically directly gets plopped onto here. So the mechanism for this reaction is very similar to the previous one. So if we have some kind of molecule like shown, I believe this was shown in the previous slide, and we react it with AlCl3, what ends up happening is that this chlorine electron is going to attack AlCl3 like in the previous problem. So what ends up happening is now we have this intermediate. We have Cl plus as well as AlCl3 attach. Now in order to get rid of this plus charge, this electron here is going to go to the Cl, thus forming this new molecule now. We have a plus charge here in the central carbon, as well as ClAlCl3. So very similar to all the other benzene reactions we've done, the last two steps is doing some kind of nucleophilic attack as well as some kind of elimination reaction. So if we have a benzene like so, and we take a strong electrophile and react it with it, so we have this molecule and we react it with the benzene, what ends up happening is that this electron on the benzene is going to directly attack this positive carbocation like so. So once it attacks, we now have a molecule that looks like this. Keep in mind that we have a plus charge here. So now the very last step, as you guys know, is doing some kind of elimination reaction. So if we take our AlCl or ClAlCl3, what ends up happening is that this electron bond is going to directly deprotonate this hydrogen, thus doing an elimination reaction. Right? So what ends up happening in the end is we now reform aromaticity like so. We have this molecule on the benzene, as well as resulting in HCl, as well as AlCl3. So this is the general mechanism for Friedel-Crafts acylation. So while Friedel-Crafts seemed like a pretty good reaction to add on any carbons to a benzene, there are also a couple problems with this reaction. The first main problem is carbocation rearrangements. So in other words, with any rearrangements, this is primarily determined on the intermediate. So just kind of judging here, you know that from the mechanism that you're probably going to create a positive carbocation here, and the Cl is going to disappear, right? And if you don't get it right now, don't worry, I'll draw the mechanism in the next slide. So because this Cl disappears, this is now a primary carbocation. However, if we look right adjacent to it, this is a secondary carbon. So because of this, there's probably going to be some kind of hydride shift, thus doing a rearrangement. So now if we try reacting a benzene with that molecule or that strong electrophile, right, like so, right, you guys can work out the mechanism on your own. However, what the resulting molecule is going to look like is something like this. And as you can see, this substituent is very different from the original substituent that we had, which is just a straight alkane chain, right? So the question becomes, is there any way that we can somehow synthesize this molecule, right? Rather than just having some kind of branch, two carbons branching out of the central one, is there any way we can have a straight carbon chain? And the answer is yes. So the way we can synthesize this molecule is by using Friedel-Crafts acylation over alkylation. And if you guys don't remember, alkylation is when there is no double bonded oxygen, whereas acylation is when there is a double bonded oxygen on the carbon. So the way we can synthesize this molecule is by using a benzene and reacting it with using Friedel-Crafts acylation. So more specifically, using a molecule that looks like this. So the reason why we can use Friedel-Crafts acylation is because this double bonded oxygen actually prevents a carbocation rearrangement from happening. So mechanistically, what happens with Friedel-Crafts acylation is if we have a molecule that looks like this, and we react it with AlCl3, right? As we all know, the first step of the mechanism is the chlorine attacking the AlCl3. Thus, this results in a molecule that looks like this. and don't forget your plus charge on the chlorine. So the next step is having this bond break, thus resulting in the carbocation being on this carbon, right? So what you might notice is that if this were to be a Friedel-Crafts alkylation, there would be no double bonded oxygen, right? And as a result, a hydride shift would occur. However, keep in mind that this oxygen has two lone pairs of electrons. So because of that, this molecule can actually undergo resonance. So what happens is that this electron can go down here, thus resulting in this resonance structure. Specifically, now we would have a triple bonded oxygen with a plus charge. So because of this, this actually prevents a hydride shift from occurring. So just like any other benzene reaction, the next step is to do some kind of electrophilic attack. So what ends up happening is if we react a benzene with a molecule that we just produced, right? Don't forget there are lone pair of electrons and a plus charge on the oxygen. What ends up happening is that this lone pair of electron on the benzene is going to attack this carbon. And because of the octet rule, this electron is going to move back onto the oxygen, right? So, as a result, this forms some kind of molecule that looks like this now. Don't forget we have a plus charge on the benzene, and we have a 3-carbon chain with a double bond on this carbon. So if you need help determining how many carbons there should be, always remember to count number of carbons. 1, 2, 3, 1, 2, 3, and don't forget that on carbon 1 there's a double bonded oxygen. So now the last step is to reform aromaticity, and as you know, this is done by some kind of elimination reaction. So keep in mind we have a hydrogen here, and we still have excess ClAlCl3. So mechanistically what happens is that this bond attacks the hydrogen, and this electron goes back onto the benzene. So as a result, we now form some kind of molecule like so. As you see, this reforms aromaticity. We have this molecule now. Keep in mind we still have HCl as well as AlCl3. So now kind of the last step is to get rid of this double bonded oxygen. And you're going to be learning this in the future unit, but basically one very good way to get rid of that double bonded oxygen is to do some kind of reducing reaction. So specifically, there are two reducing reactions you're going to learn in the future. The first one is called the Wolff-Kishner, right? And the second one is called Clemmensen reaction. Each one has a specific, scenario in which you would use it, but in this case, any would be fine. So, specifically with Clemmensen reaction, you would be reacting it with zinc as well as HCl, so Zn, Hg, HCl. So I'll use this for this example. And what this basically does is that this basically gets rid of this double bonded oxygen. So as a result, we now have a molecule that looks like this. And this is kind of the essence on how you would prevent a carbocation rearrangement. So the second problem with Friedel-Crafts is that any strong electron withdrawing groups on the benzene prevents Friedel-Crafts from happening. So specifically NO2, which I'll teach in the next video, that is a strong electron withdrawing group. And because of that, when you try reacting it with some kind of Friedel-Crafts reaction, there's going to be no reaction.